Okay. So once again, we're going to be going over sample questions from chapter 14, and also we'll be going over chapter 16 today. All right, so let me just go back to the Cengage ebook for a second and see if I can find the what I'm looking for. So, I'm having some difficulty with getting onto the ebook today. Cengage is probably, I don't know what their problem is today. Hopefully I can find what I'm looking for. All right. Yeah, there's something wrong with Cengage today, but I'm gonna try to work around it. Give me a second. I can find the pages where the sample questions are. Here we go. All right. So in your textbook itself, I'm going to be on starting on page 323. And this is chapter 14, page 323. All right, and we're going to look at question number 9 first. All right, it says, for each of the following situations, state whether the relative frequency interpretation or the personal probability interpretation is appropriate. If it is the relative frequency interpretation, this is, of course, a probability. Specify which of the two methods for finding such probabilities would apply. All right. I think we should just say whether it's relative frequency or personal probability. I think that's good enough. Let's look at A. If a spoon is tossed 10,000 times and lands with the rounded head face up on 3,000 of those times, we would say that the probability of the rounded head landing face up for that spoon is 0.30. So the question is that the relative frequency approach or the personal probability approach? Anybody can just speak out. Actually, you don't see this, do you? Hold on one second. Nobody's saying anything. I have to share that with you. So hold on. There we go. All right, now you should be able to see what I'm looking at. All right, number 9. I read through it. So it's giving this scenario here. If a spoon is tossed 10,000 times and lands with a rounded head face up on 3,000 of those times, we would say the probability of the rounded head landing face up is about 0.30. Is that the relative frequency approach, or is that the personal probability approach?
Relative frequency?
Yeah, relative frequency approach, right? It's an experiment, right? You're actually doing an experiment, repeating it many times. That's relative frequency approach, right? And in this case, we're observing the relative frequency. I think that's what we're doing, okay? We can't determine upfront what the probability of spoons landing face up is, right, when we toss it. So we have to run this experiment to come up with an estimate. Okay. All right. How about the second one? In a debate with you, a friend says that she thinks there's a 50-50 chance that God exists. Is that relative frequency, or is that personal probability approach?
Personal probability.
Yeah, of course, right? No experiment here. You're just coming up with an answer. All right, so that's it. So just be familiar with the difference between relative frequency and personal probability. I think it's pretty easy to make that determination. Let's look at number 11. Use the probability rules in this chapter to solve each of the following. Part A. According to the U.S. Census Bureau in 2012, the probability that a randomly selected child in the U.S. was living with his or her mother as the sole parent was 0.244, and living and with his or her father as a sole parent was 0.04. And what's the probability the child is living with just one parent? So what is your answer for that?
Point, oh, that's 11, right?
Uh-huh.
4?
0.4. Okay. How did you come up with 0.4?
I said 0.284.
284. Okay.
I just added them because rule number 2 is add for
Yeah. Yeah. Now you add them for what reason? They are what to each other?
mutually exclusive.
Mutually exclusive, right? If you only have one parent, it's either going to be mom or dad, or I mean, it could be somebody else, but it's always, if it's just one person, it's somebody mutually exclusive from anybody else. Yeah. So in this case, the word or, right, is used, which means add. So we add these two probabilities and we get 0.284. All right, how about part B? In 2010, in the US, the probability the child would result in twins was 0.0331. Probability that a birth would result in triplets or more was 0.0014. What was the probability that a birth in 2010 resulted in a single child? In other words, birth was just one baby coming out instead of more than one. So what's your answer to that?
Would it be 0.204?
0.204. Okay, how did you get that?
I'm not sure if this is right, but I just subtracted the 2.
Okay, this is a different question than part A, isn't it? Part B is completely separate from part A, completely separate. So we don't use data from part A because it's dealing with parents, right, of children. Part B has to do with the type of child that comes out of the womb, whether it's a single child or a twins or triplets or more. So it's asking, yeah, go ahead.
0.9655.
That's correct. Now, how did you come up with that?
I added the 2 and then subtracted from 1.
Correct. Now, when you add the two together, you're basically coming up with the probability of having at least 2 kids coming out right at the same time, right?
Yeah.
Right. So to have one child is 1 minus that. Yeah, because you either have one child or you have more than one child in a birth. And both of those have to add up to 1, those two probabilities. So 1 minus the probability of having more than one child is the probability of having one child. So you're exactly right. You add these two together, 0.0331 and 0.0014, and then subtract that from 1, and you get the answer to part B. Good. All right, so let's look at question number 12. All right, now it's referring to a figure 9.1. I guess I'm afraid to actually go. And 9.1, by the way, is a pie chart, if I remember. And it shows, I mean, you could go to it. I'm afraid to go to it and have difficulty coming back. It shows that 17.8% of Caucasian girls have green eyes, and that's one of the pieces of the pie. And another piece shows that 16.9% of them have hazel eyes. Okay. So question number 1 is, what is the probability that a randomly selected Caucasian girl will have green eyes? Please express it as a decimal. Right? So the pie chart was really, I believe, a survey, and we're sort of estimating what the population is, what percentage of the population of these girls have green eyes, hazel eyes, brown eyes, whatever. So based on
0.178.
0.178, correct. You're converting the percentage into a decimal. You divide by 100, right? Right. So 17.8% of the girls have green eyes. So we're using that as an estimate for the whole population. So we select at random girl from Caucasian girl from the population, and we say what's the probability she has green eyes, and we use that percentage expressed as a decimal, 0.178. How about part B? What's the probability that a random selected Caucasian girl will have hazel eyes?
.169.
Right. That's just 16.9% divided by 100. How about C? What is the probability that a randomly selected Caucasian girl will have either green or hazel eyes? We assume that those two types of eyes are mutually exclusive. In other words, there's not people who have one eye as hazel and one eye as green. We assume that you either have both green or both hazel.
.347.
0.347, right? You add these up, right? Mutually exclusive. Yep. We're assuming that. What is the probability that a randomly selected Caucasian girl will not have either green nor hazel eyes? Or hazel eyes.
.653.
That's right. It's just 1 minus the answer for C, right? Good. All right, so you're all doing well. That's good. Look at question number 12. Actually, we just did 12, didn't we? No, wait a minute. Yeah, we just did 12. Let's look at question, let me see, 14. It says there's something wrong in each of the following statements. Explain what is wrong. This has to do with the idea of probability. So part A, probability that a randomly selected driver will be wearing a seatbelt is 0.75, whereas the probability that he or she will not be wearing one is 0.30. What's wrong with that statement?
It's larger than 1.
Right. The two are together should add up to 1 because that's it, right? You either are wearing a seatbelt or you're not. Those are all possibilities. So probability should add up to 1, and they add up to more than 1. So that's what's wrong, right? How about part B? The probability that a random selected car is red is 1.2. What's wrong with that statement?
There can't be 120%.
Right, right. The largest probability value is 1, right? Which means certain. It can't be bigger than 1. C, probability that a randomly selected car is red is 0.20, whereas the probability that a randomly selected car is a red sports car is 0.25. What's wrong with that statement? And there is something wrong with it, by the way.
It's less than 1. Well, it has to be between 0 and 1. Never mind.
Okay, no problem.
A red sports car is more specific, but it's more common.
A red sports car is more specific, but more common than what? More common than what?
Well, it includes the red car.
Red sports car includes the red car. Okay. So why, based on what you just said, why is C incorrect?
The subset can't be larger.
Okay, which one is the subset in this case here?
The red sports car.
That's right. If a car is red, it includes cars that are not sports cars. So the probability, I think that's the first person who said this. I think that's probably what you meant. The probability that a randomly selected car is red has to be bigger than 0.25, right? Because it's including not just red sports cars, but cars that are not that are red but are not sports cars. So that's why this statement can't be true. All right, let's look at number 19, which is on page 324. Give me a second, let me turn to the page. And let's scroll down. Oops. Too far. There it is. On any given day, the probability that a randomly selected adult male in the United States drinks coffee is 0.51, and the probability that he drinks alcohol is 0.31. What assumption would we have to make in order to use rule 3? That's a multiplication rule, by the way, to conclude that the probability that the person drinks both is 0.551 times 0.31 is 0.158. So what assumption do we have to make? And once you state that assumption, do you think it holds in this case?
They're that they both can be dependent.
On
What?
what? You say dependent?
Independent of each other.
They're independent. All right, that's the assumption. And why? And do you think it makes sense to hold that we can use this assumption?
No, because just because they drink coffee doesn't mean they drink alcohol regularly.
Okay. Somebody, all right. Can you clarify that a little bit? Not sure what you mean by that.
They both seem like independent. Like they're not.
Oh, you think they're independent? Okay.
I think.
All right. Does anybody disagree with that? Can you explain can anybody explain what independence means? What does that mean?
One doesn't affect the probability of the other happening.
Right. So do you think these two are independent of one another?
Yeah, I think they're independent.
Anybody else? All right, I would argue in this case, I think they're dependent. And the reason is if you've been drinking alcohol and you want to become sober, it's more likely you're going to drink coffee. Okay. There's some, to me, there's some relationship between the two. They're not completely independent of one another. So the probability of drinking coffee actually will go up if you've been drinking alcohol, if you're trying to recover from the effects of alcohol. So using that reasoning, I would say they are dependent. Of course, you'd have to actually look at the data, right, to see if it's true or not. But you can argue both ways. I was just not interested in the argument why you would think they were independent. But I think there's some dependence between the two. Okay. Just my own opinion on that. How about, now we're going to scroll down number 32. All right. Now, it says here in the 3-spot version of the former California Keno lottery game, whatever, the player picked 3 numbers from 1 to 40. 10 possible winning numbers were then randomly selected. It costs $1 to play. The accompanying table shows the possible outcomes. Okay. Compute the expected value or the net gain for this game, and then interpret what it means. So this is where you probably need a calculator next to you to do this. So let's take a minute. I want you to work on this. So these are the possible winnings. Okay. Now, when they say matches, they're matches to what? The three numbers, right? You get all three numbers, you win 20 bucks. You get two of the three numbers, you get $2. And if you got 0 or 1 of the numbers, you don't win anything. Here are the respective probabilities of those three possible cases for this game. So the question is, the expected value or net gain for this game. This is for the person who's playing the game. You have to remember that the answer has to be negative, right? Because the lottery commission, whoever's California Lottery Commission's got to make money from this. So who's going to end up losing money? It's got to be, on average, the person playing. If anybody has an answer, let me know. It's okay to use a third decimal point on this. You don't need to round it or anything. Just tell me what the answer is.
Negative 49 cents.
Okay, you rounded the 2 decimal points, right?
Yeah.
Yeah. Was it negative 0.486? Is that what you got
Mhm.
originally?
Yeah.
Okay. Okay. So tell me how you did it.
I multiplied the probability of matching 3 or 2 by the amount you would win, and then I added them up and then subtracted that from 1.
Okay. Subtracted that from 1. Okay.
Or 1 subtract from that amount.
Oh, all right. Because you played because it cost $1.
Yeah.
Sure. You could do it that way. Certainly will work. Let me show you a little table I created. Just stop sharing for a minute. Go to PowerPoint. I'll post this, by the way. I think I've already posted it. Here's number 32. So this is how the book does it too. You can put your gain in the upper row here, and then the probability in the lower row. So if you won $20, your net gain is 19.
We can't see the table, Professor.
That's right, because I didn't switch over. Okay. Share it. Now you can see it, right?
Yep.
Sorry about that. Now, I put gain in this table. I put gain on the top row, probability in the bottom row. Gain is just your net gain. So if you are a $20 winner, your net gain is 19 because you paid $1. Okay. And the probability is below here, 0.012. It's probability of winning $20. Probability of winning $2 is 0.137, but your net gain is $1 because you paid $1. So 2 minus 1 is 1. Now, if you didn't win at all, well, the probability of not winning at all is 0.851. And because you didn't win anything, but you paid $1, your net gain is negative $1. Then you just multiply the net gain times each probability. So net gain times its own probability for each one of these three things. That's what I did here. Add them up. And that's where you get negative 0.486. Right? So it's about, you're losing almost, you're losing 49 cents on average per gain. So that's what the, by the way, that's what the long-term, thing means here. This average is over the long term. A randomly selected player loses almost 50 cents per game. Does that mean that's what you get on a particular game? That's what you lose? No, of course not. You either win the game or you lose the game, right? You either win $20, you win $1, you lose in any game. But over the long term, this is what your expected loss is going to be. Now, what's the expected gain for the person running this per person per game? What's their, so the commission or whatever, whoever's running this game, what's their expected gain per game per person?
0.514.
No. You're thinking in terms of probabilities. This is not a probability.
Oh,
So if the on average over the long term, if one person's going to lose around 49 cents, what's the average gain for the person running the game?
49 cents.
49 cents positive, yeah. And if you know you had 50,000 people playing this game, you would just multiply this times 50,000. That would give you what? The expected number of or expected amount of money that you would have to that you win, that you earn as a administrator of this game. You're going to win that much. All right. So that's why casinos exist. That's why lotteries exist, is because whoever's running it's going to make money. And there's going to be people losing, right? Money, and there's going to be people winning money from this game. People play it because they want to win the $20 or the $2. That's why they're playing it. But most people are going to lose. And so overall, the overall average is a loss of about 49 cents per person per game, which means that's how much the casino or the government is making on this game. All right, 34 is the next one. Let's go back to the book. Go to number 34. According to the U.S. Census Bureau in 2012, about 68% of children in the U.S. were living with both parents. 24.4% were living with mom only. 4% were living with dad only. 3.6% were not living with either parent. What is the expected value for the number of parents a randomly selected child was living with? So this is a little more complicated. You have to think about it. When they say expected value, they're talking about the average amount over the long term, just like what we just did. So what do you need to determine expected value? You need values to list and their respective probabilities, right? Because to find expected value, you multiply the value times the probabilities and add them up. So you need to create a chart like I just showed you for problem 32. You need to create a chart for this one here, where you're finding the expected value for the number of parents a randomly selected child was living with. An overall long-term average based on these numbers that are shown up here. So this is a little harder question, but not beyond what you guys can do. Okay, so anybody, I'll give you a minute and then somebody can yell out what you think the answer is. Please, the answer should be to 3 decimal places. Don't round it any higher, more than that. 3 decimal places. Anybody have any answer? The expected value or average of the number of parents a randomly selected child was living with. So the answer has to be between 0 and 2, right? Because those are the three possibilities. You either were living with nobody, living with one parent, or you're living with two parents. I don't hear anybody saying anything, so let's move, let's show you the solution. Okay. So that is your, those values for the number of parents that child lives with. It's either 0, 1, or 2. Now it says in the problem, it says that there's a 3.6%. Is that what it was? 3.6% of the children don't live with any parents. They did mention what? They mentioned that if there was 24.4% living with mom only and 4% living with dad only. You add up those two numbers, you get 28.4% or 0.284, it's your probability of living with one parent. You're either living with mom or you're living with dad. So you add up those two probabilities, get 0.284, and then 68% of the children live with both parents. So that's 0.68 for 2. If you add these three probabilities up, they do add up to 1. Okay. Now you simply multiply these values, these 0, 1, and 2 by their respective probabilities. Now 0, of course, times the probability is going to be 0. So you're literally just adding up these two. 1 times 0.284 is 0.284. 2 times 0.68 is 1.36. You add up those two numbers, you get 1.644 parents. So that's the expected number of parents overall over the long term, 1.644 parents. See how that works? All right, so you have to think about when they say expected value, you have to think about expected value of what? In this case, it's the number of parents a child lives with. So you put down all the possible values. It's either 0, 1, or 2. And then you put down the probabilities. This one in the middle here with 1, you have to calculate that because there was two parts to it. There was part with living with mom only, and there's the part with living with dad only. So you have to add up those two probabilities to come up with this number. But these two numbers here were given in the problem. And then you just simply multiply the value times the probabilities and add up the products. That's how you come up with the answer. That's 34. All right. Any questions about that? So those are the sample questions from this chapter. Obviously, I'm showing them to you so that on your next test, you may have some problems that may look like this. So that's why I'm showing it to you. So you have this on your, it's in the in Canvas. It's included in Canvas right now. Sorry. There we go. All right. Any questions about any of these problems that we went over? Yeah. All right. So what we're going to go over today is chapter 16. Now, 16 has no real calculations in it, but it has to do with personal probability. And we talked about the two types of probability, the relative frequency approach and the personal probability approach. The relative frequency approach is what we just were doing. We were calculating probabilities. And that approach, everybody should get the same answer when you do your calculations, all right? You should get the same. If you're looking at the same data, you're going to come up with the same probability. Personal probability, everybody will come up with different answers, right? Because it's personal. So in this chapter, we're looking at what may influence your personal probability. the types of things that could influence it. And there's been a large body of research on this area. It's been done over the last 40, 50 years. And the area that we're talking about here is deals with the types of biases that we're wired, that our brain is wired in a certain way, and then we tend to look at things in kind of biased ways. So our personal probabilities are influenced by these different biases. So that's really what this chapter is about, just to introduce you to some of these biases. So let's look at this first thought question. It says during the Cold War, now the Cold War, for those of you not familiar with that term, is dealing with before Russia and Ukraine all became separate countries. It was the Soviet Union. And the Cold War was between the US and Soviet Union, possible nuclear war, that sort of thing. That's what they're referring to. All right. During the Cold War, this author presented readers with the following test. Place a check mark beside the alternative that seems most likely to occur within the next 10 years. So they have two different possible scenarios here. Number one is an all-out nuclear war between the US and, they say Russia, but would have been Soviet Union. And number two here says an all-out nuclear war between the US and Russia, in which neither country intends to use nuclear weapons, but both sides are drawn into the conflict by the actions of a country such as Iraq, Libya, Israel, or Pakistan. So it says here, use your intuition, pick the more likely event at that time. So picture where there was a lot of tension between the US and Russia, and they're asking what is more likely to occur, A or B? So what would be your answer?
A.
A. An all-out nuclear war between US and Russia, more likely than the B here, right? And what's your reasoning?
I mean, A includes the answer B, so.
Right. So you have just learned from chapter 14, right? That A here is a bigger set of possibilities than B. B is just a subset of A, right? But most people, if they have not learned chapter 14, would pick B. And why? It's because it's more detailed. And they can picture it more. So let's say, B is more likely, just because it tends to bring up images to them. So this is something we'll be talking about, how sometimes, unless you're prompted one way or the other, you go with the one, you give the higher probability to the one that's less likely to happen. Which is more likely cause of death in the United States, homicide or diabetes? So why don't you guess at that one? When you answer these, try to just answer what pops into your head first.
Homicide.
Right. Whoever just said that is honest person. That's what popped into your head first, right? The answer is diabetes. Diabetes is very high percentage of people that die from that. Much fewer number of people die from homicides. And yet the reason for this is why? Because you hear about homicides all the time. You don't hear about people dying of diabetes. We're going to give a term for that in a few minutes. You think people are more likely to pay to reduce their risk of an undesirable event, to reduce their risk from 95% to 90%, or to reduce it from 5% to 0? What do you think more people are likely to pay? Are they going to pay more for reducing their risk from 95 to 90% or from 5% to 0?
5 to 0.
Right. Okay. That is what most people would say. Probably the vast majority of people would say that. And yet the reduction in risk is 5% for both cases. So we're going to learn why most people pick from 5% to 0 in a minute. But thank you for, again, giving an honest answer there. All right. A fraternity consists of 30% freshmen and sophomores and 70% juniors and seniors. Bill is a member of the fraternity. He studies hard. He's well liked by his fellow fraternity members. He will probably be quite successful when he graduates. Is there any way to tell if Bill is more likely to be a lower classman or an upperclassman?
Upper,
Okay. Why is that?
because he's well liked.
Okay. Anybody else? So you were, whoever was saying this, you were looking at his description, right? Well liked, and you came to the conclusion that he must be older, right? Is that right? More experienced, older?
Yeah,
Did you consider the 30% and 70% here at all?
well, yeah, if there's more upperclassmen, it would make sense for that too.
Yeah. What if these numbers had been reversed? What if it was 70% freshmen and 30% juniors? Would that
I'd
have
probably
influenced
still
your
go with
answer?
well liked.
What's that?
I'd probably still go with
You
upperclassmen.
still go with upperclassmen, right, right. So that's what there's another bias in here, right? You're being influenced by the description here, as opposed to the actual numbers. The answer should be Bill is upperclassman just because of why? Just because
Because of the
70%, yeah. And there's nothing in the description here which really tells you whether they are younger or older. You're just sort of like looking at it and you're kind of picturing it, right? But there's nothing in here that's really leaning one way or the other. So you're sort of coming up with your own conclusions based on what you're reading. All right, this all has to do with personal probability, how it can change based on circumstances, right? Sometimes personal probability will change over time. You may see, somebody may ask you the same question in terms of probability one day and then maybe a month later, and you may not remember how you answered it before, and you come up with a completely different probability than you did before. So personal probabilities are very flexible and are influenced by conditions in the environment and also by your own personal biases. But you still have to follow the rules of probability. Probabilities have to still be between 0 and 1, right? You still have to follow the mutual exclusive idea of adding and the independent idea of multiplying, okay? So in the book, they come up with these different types of biases that, again, influence your personal probabilities. And one of them is called the certainty effect. Right? This is the effect where you would be willing to pay more for certainty. Let's say to reduce your risk from the fixed amount to down to 0. That was one of those questions we asked in the beginning, right? Where you were more likely to go from 5% down to 0, which is certain, right? Than to go from 50% down to 45%. The same drop, the same amount of a drop, but you're willing to pay more for the certain result. And that's what they're talking about here, probabilistic insurance. All right, where some people are willing to pay, where something costs half as much as regular insurance, but only covers losses with 50% probability. People aren't interested in that. This has to do, by the way, with, let me give you an example, a warranty. You know, you buy some expensive item and then they have a warranty attached to it. So let's say something like, the warranty will be half as much as a regular warranty, but only cover 50% of the losses. Or the other possible type of warranty is it costs obviously twice as much, but you're guaranteed losses for half of the possible types of losses that you can have. almost everybody picks the second because they like the idea of certainty. They'd rather have a warranty that 100% of the time covers certain types of losses, and they're willing to pay more for that. All right, so this is the idea of the certainty effect. People are willing to pay more than they should because of the idea of certainty. All right. You can read about it more in the book. The book gives more detail about this. And then there's this thing called the pseudo certainty effect, similar to the certainty effect. Because people are more willing to accept a complete reduction of risk on certain problems and no reduction on others than to accept a reduced risk on a variety of problems. This is a more like the warranty situation I talked about. That's the same idea. Here's an example also of the pseudo certainty effect. Well, actually, there's both of these effects here, but they're very similar. Here's a vaccine available for a disease that afflicts 20% of the population, but would protect with 50% probability. All right. So it's here's a vaccine. Maybe this is like COVID vaccine or something, right? It afflicts 20% of the population, but would protect with 50% probability. It says here maybe 40% of the people would take that vaccine. Suppose there are two strains of this disease, right? Two of the virus. Vaccine completely is effective against one of the strains, but there's no protection against the other one. Okay. It says here, more people would take that vaccine. More people would take the vaccine. Although the risk is about the same. The reduction in risk is about the same. People will go for the second case because of the fact that with certainty, they're protected against one of the two strains of the virus. They prefer that situation than to the first situation where you have 50% probability of being protected from the disease. All right. So this is the whole idea of certainty or pseudo certainty. People are willing to not pay more. In this case, not pay more. People are attracted to situations where there is certainty to the result. Okay. All right. There's this term in the book called a heuristic. This is how this word is pronounced, heuristic. Heuristic is some mental bias. It's some sort of way that our brain works, that it makes us look at the world in sort of a distorted way. Okay. And there's one type of heuristic called the availability heuristic. All right. Now, what does that mean? Let's look at this question here. Which do you think caused more deaths in the United States? This is similar to what we said before, homicide or diabetes. And somebody in class mentioned homicide. The answer is actually diabetes by much higher. For example, it says, this is back in 2000, but it's probably the same, similar now. The actual death rates per 100,000 people with a homicide is 6 per 100,000. And the number of people dying per 100,000 from diabetes is 24.6. So it's 4 times higher. And yet people inevitably pick homicide because it's more familiar to you. All right. You see more stories about homicides. You don't hear anything about diabetes unless you have a family member who has it. So this is called the availability bias because this information about one of the choices is available to you and the other choice is not. And you don't even think about probabilities at all. It just comes to your awareness and you go with that. You go with that, whatever comes to your awareness. All right. So risk perceptions distorted by having people vividly imagine an event. All right. This is another type of distortion. Here's an example. Salespeople convince you that $500 is a reasonable price to pay for an extended warranty on your new car. by having you imagine that if your air conditioner fails, it will cost you more than the price of the policy to get it fixed. I know, again, I don't know if any of you have been to a store and bought a major item, obviously not with the pandemic recently, but let's think about last year maybe, right? You're buying something and somebody's trying to sell you a warranty. Well, inevitably, they say what to you? They say it's going to cost you more than that amount to get something fixed, right? They always tell you that. And you may be convinced and you buy the warranty. What you don't realize is what the expected loss is going to be over the long term. The probability of that item failing is probably very low, right? And the probability of it not failing is probably very high. If you find the expected loss, it's probably much smaller than the amount that they are asking you to pay for the warranty. That's why most places, most publications tell you don't buy warranties for anything, because over the long term you're going to be throwing money away. It's a big money make. By the way, if you ever buy a car, don't try to stay away from warranties, because the warranties are there they're almost like free money to the salesperson. Because overall the company makes lots of money on warranties. So try not to buy a warranty. But people buy them because of the fact that the information in your head is you're being told information by the salesperson, which influences or distorts your perception of risk. All right. And that's why you buy the warranty when you probably shouldn't buy it. Here's another one called anchoring. Anchoring is, again, used by people in public life, by salespeople, by companies, politicians, whatever. And they try to distort your perception by giving you a reference point from which to make your decision. Okay? This is a very popular way of trying to influence people. But here's an example here. What's the chance of nuclear war between the US and the Soviet Union? So here are two anchors here that are given to people. In the way the question is phrased. Number one, it says, do you think the chances were higher or lower than 1%? Well, they're giving you a number here. Most people will give the answer around 1%. They'll give a single-digit answer. Or if it's two-digit answer, it's going to be close to a one-digit answer. All right? Because they're giving you, and it's probably because you don't have no idea, but if they give you a number, you're going to shoot for some number around that number. If somebody said, do you think the chances were higher or lower than 90%, you're going to pick something much higher, because this is the only number that you have a reference to. If they don't give you any choice, then it'll be all over. You know, people's answers will be all over the place. So some of them will be low, some will be high. But in general, if you do research on this, you'll notice that the high anchor estimates are on average higher than the no anchor estimates, which are higher than the low anchor estimates in this case here. So be careful with anchoring, because it can influence your answer. There's another one called the representativeness heuristic, something related to it called conjunction fallacy. Representative heuristic leads people to assign higher probabilities than warranted to scenarios that are representative of how we imagine things would happen. Those we have we come up with some idea of the way things should come out, and we come up with a higher probability of that than it really is. Another one's called the conjunction fallacy. Conjunction fallacy is people tend to give a higher probability of two things happening at once, because again, they can imagine the two things happening together, when in reality, if they're independent of one another, the probability of two things happening together will be smaller, not bigger, not higher. So let's look at an example of this. let's read about Linda here. Linda's 31 years old. She's single, outspoken, very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Respondents were then asked which of the two statements were more probable. Number one, Linda is a bank teller. Number two, Linda is a bank teller who was active in the feminist movement. This was asked to people, undergraduates. This study's been done over and over again. It's pretty famous. 86% of the people said the second one is more probable. All right. And when they say statistically naive, that means you haven't been studying statistics, right? So you haven't been going through chapter 14 at all. You don't know about chapter 14. 86, that's almost 90% of people will pick the second one. Why? Because they look at the wording here and they say, well, she's kind of interested in going out and being an activist, right? This shows she's like an activist. And then you look down here and you see active in the feminist movement. She says, oh, that sounds about right, right? And you're going to pick number two. More probable than she's just a bank teller. That sounds boring, you know. She's just a bank teller. She sounds like a boring person, but she's active in the feminist movement outside of work. That sounds more likely. So you pick number two. And yet number two is a subset of number one, right? Because you have bank tellers who are not active in the feminist movement. But people don't think probability in terms of probability. They think in terms of likelihood based on information that they're given. So this is called representativeness, right? It's a bias that's based on what? Based on what you know about a person, about an event, whatever. And you're basing your judgments about probability based on what you know about that situation, what comes to mind. And if you see active in the feminist movement, and you see up here she's been active in other types of demonstrations, then you think this is number two is more likely. So you're not answering the question in terms of probability, you're answering in terms of likelihood. And the answer should be one, has to be more likely. So this information up here is biasing you to choose number two. That's called representativeness. Okay. All right. There's another one that has to do with forgotten base rates. Base rate. What is a base rate? It's a rate from which you start. This is another form of representativeness. You can lead people to ignore information about the likelihood of various outcomes. All right. Here's an example. Subjects told a population. Subjects were told about a population has 30 engineers and 70 lawyers. They were asked, what's the likelihood that a randomly selected individual would be an engineer? Average close to 30%. All right, fine. That makes sense. Then subjects were given this description, asked the likelihood that they were an engineer. Dick's 30 years old. He's married with no children. He has high ability and high motivation. He promises to be quite successful in his field, or he promises to be quite successful in his field. He's well liked by his colleagues. When you read this, most people, again, who are not studying probability, will ignore the 30-70 comparison here. And what would they say? They're going to give an answer closer to 50%. There's a 50% chance that they're an engineer. Because they're reading this and they're saying, well, this could apply to both an engineer and to a lawyer, right? And I'm not so sure which one it is, so I'm going to say 50-50. And they ignore this fact that there's 30 engineers and 70 lawyers in the population. They completely ignore that. So they forgot about this base rate, this 30 engineers and 70 lawyers. They forgot about that, and they're influenced more by the words of the description of the person. Okay, any questions about any of these biases. Now, the next ones I think are kind of straightforward. Optimism. Okay. If a person is optimistic about their ability to make choices, they're always going to be more optimistic than they should be, right? It's just according to these people here who did some research, they said the great majority of individuals believe themselves to be better than average drivers, or likely to live past 80, less likely than average to be harmed by products they use, and so forth. In other words, most people are above average. Now, you know, average, right, means when you take an average of numbers, some numbers are going to be above, some numbers are going to be below. But you know, you read about any product or anything that's being sold out there, they always say that we're better than average. Well, that can't be true, right? Not everybody can be better than average on anything. Some people are going to be better, or products are going to be better. Some things are not going to be as good as average, just because that's the way averages are calculated. They're in the middle of what numbers are. You know, when you average numbers, some numbers are going to be higher, some numbers are going to be lower. So optimism tends to apply to almost everything. People tend to be overly optimistic. Of course, they could also be overly pessimistic, but that's not true for most people. Here's an example. On the average, students rated themselves as 50% more likely than others to experience positive events and 20% less likely to experience negative events. Right? And of course, just that cannot always be true. Another thing that people are reluctant to do is change their beliefs, even when there's evidence to the contrary. This is called conservatism. The tendency to maintain your probability estimates even when new evidence comes across that should change it. People are resistant to change. That's what this is basically saying. Also, overconfidence. People tend to be too confident in their assessments, right? So they overestimate the probability that they're correct, underestimate the probability that they're incorrect, right? And this is just an example of this sort of thing. So we'll see how we're doing with time. We have 5 more minutes. Okay, it's about done. In this study, they asked people hundreds of questions in general knowledge. What type of magazine do you read? I don't know if people read magazines much anymore, but Time magazine, Playboy. They were also asked to rate odds that they were correct. Remember how we calculate odds? 1 to 1 means 50-50 chance. 1,000,000 to 1 is almost certain. It says here, the more confident the respondents were, the more the true proportion of correct answers deviated from the odds given by the responses. In other words, the respondents underestimated the true odds if they were overconfident, okay? And this, again, common sense that when people are overconfident, they tend to overestimate positive things and underestimate negative. That's pretty much what they're saying here. In this slide here, they're basically talking about how do you correct for these things. You have to be aware of your personal probability biases. You should use, if possible, relative frequency probabilities instead of your own personal probabilities. You have the example of weather forecasters and even doctors. You know, a good example with doctors would be if a test comes, and this happens a lot probably, if a test comes in and you've been sick and the test comes in and indicates that you have some ailment or something, and then you have some unusual symptoms that don't fit the ailment, doctors are sometimes hesitant to go beyond that ailment in terms of a response. They say, oh, I think it's unusual, but I think, you know, you just have this particular ailment. And it may not be true. You may have some other complications too. So doctors are also have biases. And they sometimes may be underestimating or overestimating the probability of some disease. All right, and then there's some ideas about how to improve your personal probabilities. All right, so let me give some particular ones here. All right, you can read through these. All right. So again, this chapter has to do with personal probability, the different biases that we could fall into, which could lead to distorted probabilities, which are different than the true probabilities. So these are, in this chapter, you just have to be familiar with these different words, what they mean. And obviously next week's quiz, chapter 14, obviously easier to define the different types of definitions. But again, it's open book. So what I'll do for this chapter, when I ask for quiz questions, is I'm going to pretty much take things word for word out of the book. All right, word for word, and just ask you to put in the type of heuristic or the type of bias that it's referring to. So it should be, I would think, a pretty easy quiz, because there's I can't get too complicated with this. All right, and that's it for 16, chapter 16. We were supposed to cover chapter 17 today, but we'll cover that on Monday, next Monday. Then we're also going to be on next Wednesday, we're going to move into something new on sampling. It's chapter 19. But I also want to begin showing you a new software program that it's free. It's called StatKey, and you're going to be using it for pretty much the remaining part of the course. And so next Wednesday, don't miss next Wednesday, be in class, because I'll show you as part of the class how to use StatKey, because it's going to replace many of the calculations that are taught in a traditional statistics course when we do what's called inference. Inference means taking data from a survey and applying it to the population. So we're going to replace many of those calculations with StatKey, and StatKey uses it's an easier thing to use for people. So for this type of course, we're going to use this thing called StatKey. And again, I'll explain it more next Wednesday, but don't miss next Wednesday. I will have a handout meaning something that will be posted on Canvas that will be instructions on how to use StatKey. All right. It'll include not only introduction to StatKey, but also the types of things that we'll be doing in StatKey. Will be instructions in all of it. And then my job basically is to show you examples of how to use it and how to come up with the different types of things, different types of results that we usually look for in a statistics course. All right, so we'll get to that next week, but don't miss that, because otherwise you're going to be relying on reading the StatKey instructions. Better to see a demonstration in class. Obviously, you can miss it and watch it on the recording, but I think it's always better to do it in person. All right. Do we have any questions about anything I covered today? Anything from the chapter 4 problems or chapter 16, what I covered in chapter 16? Okay. So that is it for today. So I'll stop the recording.